All right, today we'll be going over the intersection of planes. More generally, what are the different ways that planes can relate to each other in three-dimensional space. So first, the definition. Two planes with normal vectors n and m are parallel if their normal vectors are parallel. That's the only case where two planes don't intersect. Think of, say, a wall, or rather a ceiling and a floor. The two are parallel, they'll never intersect. If two planes in three-dimensional space are not parallel, then they have to intersect. And the way they intersect is in a line. So we can draw an example of this. So suppose our first plane looks something like this. And our other plane looks something like this. And we see that these two planes will intersect in a line here. Now, each of these planes has a normal vector. So say that we have n for this purple plane, and then we have m for the blue plane. And so remember what a normal vector is. A normal vector just means it's a vector perpendicular to the plane. Now you'll notice in the definition there's more. If theta is the angle between these two normal vectors, we define, and we pick the smaller angle between the two vectors, we define that angle theta, the acute angle between the vectors, as the angle between the planes. So if we take these vectors and draw them over here, so say we have, this would be n, and then this would be m. Theta is the angle between these. And again, this is the angle we define as the angle between the two planes. So, types of questions that we see with two planes. 1, find the angle between the two planes. We'll do that as an example. And 2, actually find this line of intersection. So first we'll do the angle question, and then we'll come back to the picture to talk about the line of intersection. So suppose we have this example where we're given two planes. So remember, linear expressions in x, y, and z are planes in three-dimensional space. And we want to find the angle between the two planes. Well, the key then is to find the normal vector for each plane. And remember, to get the normal vector, we can just pull the coefficients of x, y, and z. So for this first plane, we'll have 1, 1, minus 1. And for the second plane, we'll call it m, we have 2, minus 3, 1. So the question now is reduced to what is the angle between these two vectors, and recall that we have a version of the dot product where it's the length of n times the length of m times cosine of the angle theta. And we also can calculate the dot product directly from the definition. So remember, multiply the corresponding components of n and m, and then add those products. So 1 times 2 plus 1 times minus 3 plus minus 1 times 1. Which is 2 minus 3 minus 1, or minus 2. That gives us the left-hand side. Here, we now want the lengths of n and m. So the length of n is the square root of the sum of the squared entries. So square root of 1 squared plus 1 squared plus minus 1 squared, or root 3. And the length of m, we have the entries of m squared and added. So 2 squared plus minus 3 squared plus 1 squared, or this is what? 1 plus 9 is 10, plus 4 is 14. So root 14. Rearranging our dot product equation gives us that cosine of theta is n dot m over the product of the magnitudes of n and m, which we just computed the numerator to be minus 2 and the denominator to be root 3 times root 14, or minus 2 over the square root of 42. So theta is the inverse cosine of negative 2 over root 42. So taking this equation, cosine theta is equal to this, so we take the arc cosine of both sides to get theta. And this won't work out to be anything nice. Okay, so that gives us an example of finding the angle. The next example will deal with finding the line of intersection of two planes. Now recall our picture here. So this is the case where our two planes are not parallel and they intersect in this orange line. We want to find the equation, a set of parametric equations to represent that line. Now, recall that for a line, we need two things. We need a point on the line, if a point is on the line, that means it's on the purple plane and it's on the blue plane. So that will boil down to finding a point that's on both planes. So that's the first thing we need. The second thing we need is a vector parallel to the line. And that's when we can notice here that we have m and n. We know, oh, I did these backwards. Oh, no, this is fine. This is right. We know that this purple vector n is perpendicular to anything in this purple plane. Well, the line of intersection lies in that purple plane. So n is perpendicular to the orange line of intersection. The same also holds for m. M is perpendicular to everything in the blue plane. Well, that orange line is also in the blue plane. So that means this line is perpendicular to both m and n. What else is perpendicular to both m and n? Cross product. So if we do, say, n cross m, we can set that to be our v. And that is perpendicular to both of those vectors, which means if it's perpendicular to both m and n, it's also going to be parallel to this line of intersection. Although I could have drawn this, I should have drawn this the other way. Just redo that diagram. So we have a right angle here and a right angle there. It was probably better the other way. In any case, the idea is this cross product is parallel to the line of intersection. So let's go back to our new example. We have two planes and we want to find the line of intersection. So the first thing we need to do is get their normal vectors. So remember, we pull the coefficients of x, y, and z. So we have 1, 1, minus 1. And then here we have 1, minus 1, 2. And our vector will be the cross product. So our vector v we can set to, say, n cross m. And of course, you can do m cross n as well. Just remember, because of the non-commutativity of the cross product, if you did m cross n, it would just point in the opposite direction, still parallel to the line that we're after. Okay, we set up our 3x3 determinant for cross product. So we have I, j, k in the top row. Then we have the entries of n, 1, 1, minus 1, and then m, 1, minus 1, 2. And we can work through this. So we have I times its 2 by 2 minus j times its 2 by 2 plus k times its 2 by 2. And remember how we do this. To get the 2 by 2 for I, we erase the column and the row containing I, and what remains is the 2 by 2 for I, which is 1, minus 1, minus 1, 2. For j, we erase the row and the column containing j. That gives us 1, minus 1, 1, 2. And then for k, we erase the row and the column containing k, and we get 1, 1, 1, minus 1. Working through these 2 by 2's, we have I times 1 times 2 minus 1 times minus 1. So 1 times 2 minus 1 times minus 1 minus j times 1 times 2 minus 1 times 1. And then plus k. We have 1 times minus 1 minus 1 times 1. This gives us, for I, we have 2 minus 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 1. So 2 minus 1, or 1. Here we have minus j. This is 2 minus minus 1. So that's 3. Plus k. This is minus 1, minus 1. So k has a minus 2. So this gives us the vector 1, minus 3, minus 2. So this is our v. This is the vector parallel to the line of intersection of the planes. Now we need to find a point on the line, we have to tinker around a bit. So let's record first on this next page that our vector parallel is 1, minus 3, minus 2. And to find a point on the line, one approach that I like to take is that line is going to intersect either the xy plane, the zy plane, or the xz plane. So one of these coordinate planes, xz plane, zx plane, or the zy plane. And the equations of those planes, the xy plane, if you think about a point being in the xy plane, its height on the z-axis has to be 0. So the xy plane has an equation z equals 0. Similarly, the zx plane, for any point in that plane, the y-coordinate has to be 0. So the equation of the zx plane is y equals 0. The equation of the zy plane is x equals 0. And so essentially we just fish for a point where the line intersects one of these planes. So we try setting z equals 0. So this, again, we want to find the line's intersection with the xy plane. If it doesn't intersect with the xy plane, we won't get a solution here, and then you just try one of the other ones. Try y equals 0. Or if that doesn't work, try x equals 0. One of them will work. So if we set z equals 0, come back to our plane equations. This first plane equation, if you set z equals 0, that z term goes away. And what's left is x plus y equals 1. For the other plane, if we set z equals 0, the 2z term goes away, and we have x minus y equals 2. And what we now have is two equations and two unknowns having fixed the z-coordinate at 0. So we solve these. So this first equation would tell us that y equals 1 minus x. We can then plug this in for y to the second equation. So we get x minus quantity 1 minus x equals 2, or x minus 1 plus x equals 2, or 2x equals 3, x equals 3 halves. Since y is 1 minus x, y is 1 minus 3 halves, or minus 1 half. So this means the point x equals 3 halves, y equals minus 1 half, and remember we started with z equals 0, is on both planes. We found this in such a way, algebraically, that it satisfied both plane equations. So just to recap, we set z equals 0. That said, let's check in the xy plane. When z equals 0, these two equations were what our plane equations reduced to. And we solved those simultaneously, giving us x equals 3 halves and y equals 1 half. So this is the point in the xy plane that is on. It is a point in the xy plane where both of these, it's on both of these planes. So the point is, if it's on both planes, then it's on the line of intersection. Right? By definition, if it's on both planes, it's on the intersection of the two planes. And so this gives us now what we need. We have a vector parallel to the line and a point on the line. And recall that our parametric equations for our line, we have x equals y equals z equals, and the coefficients of the parameter come from the parallel vector. So we have minus 1 times t. Sorry, that's a plus 1 times t. 1 times t. Minus 3t, minus 2t. And then we add the coordinates from the point. So we would have 3 halves minus a half, 0. And this gives us a set of parametric equations for the line of intersection of the two planes. And by the way, you can check pretty quickly if you did a problem like this right. Well, you can at least check some of it. You can check that this point is actually on both planes by just plugging this into the plane equations and making sure that they're both satisfied. But this is the idea. This is how we get the intersection of two planes.